In this segment, I'm going to talk about the layout of the gears and the relative sizes of the gears in the gearbox. My plan is to conclude with the preliminary design of the gearbox. The design parameters for this gearbox are small physical size, less than about 4 inches maximum dimension, lightweight, able to pass 5 horsepower with minimal losses, able to operate at 6 to 7,000 RPM, short duty cycle, should be less than about 10 minutes per hour, good exterior passive cooling, because we have a propeller in an airborne vehicle, a life of at least 100 hours of operation, low impulse loading, and it's going to be lubricated by grease rather than oil. To achieve reversal of the rotary motion, a gearbox needs an idler gear. An idler is a gear that doesn't do any work. Its function is to reverse motion, that is rotary motion. The size of an idler in a gear train does not affect the gear ratio of the gearbox as long as the input and output gears are the same size. An idler gear can be made larger, and if so, it will reduce the speed of the gears within the gearbox. But as you can see here, where I've inserted a 3-inch idler, this one has 48 teeth, but that will make the box bigger and it will add weight. Note, however, that even though this gear is larger, the larger gear meshes with the input gear because both have the same diametral pitch. This is obviously not practical for our gearbox because it would exceed the 4-inch size limitations. So let's try a different size gear. Here we have a small gear. This one has a pitch diameter of 0.75, 3/4 of an inch. And as you can see, it's very small. It's also considerably weaker than the larger gear. This particular idler has 12 teeth, but again the diametral pitch is still 16, so the gears actually still mesh effectively. This smaller idler will allow for smaller and lighter gearbox, but smaller gears must rotate at higher velocity, which will place demands on the bearings and the shafts, which are already moving at approximately 6,500 RPM. The loads on the smaller gear will also increase because it has fewer teeth. In my judgment, this combination of higher loads and higher velocities is not preferable if the gearbox can meet the design criteria without them. So let's change one more time and have a look at a gear which is the same size as the input gear. This choice is a compromise between large overall size and the higher velocities that will be necessary with smaller gears. And for all these reasons, I've chosen to use idlers at the same size as the input and output gears. This choice has a further benefit in that it allows all the gears in the gearbox to be identical, which will make building them considerably less complex. Now the next thing that we have to achieve with this gearbox is contra rotation. We know that both shafts must be coaxial. We also know that the input shaft and one of the output shafts are turning in the same direction at the same velocity. Therefore, it seems prudent to use the input shaft as one of the output shafts. Here we've shown the inner shaft. On the bottom of the inner shaft is a plate whose purpose will be to connect the inner shaft to the motor. The shaft is initially 0.25 inches in diameter, and it's approximately 6 inches long. To this I'm going to add what I'm going to call the input gear. As shown, the input shaft is connected to the motor, and it's unbroken as it goes through the gearbox from the motor side to the propeller side. The gear that I've called the input gear is fixed to the input shaft. We can add an idler gear, the first idler gear, so that it meshes with the input gear. Now, as the input gear rotates clockwise, the first idler gear will rotate counterclockwise. The next thing we need to do is somehow transfer that reverse rotary motion to the output shaft. But note, however, that the output gear is on a different plane of rotation than the input gear and the first idler. And I've done that so that they don't interfere with each other. Now, if we could just connect the idler to the output shaft, we'd be done. If we were to do something like this, the two gears would be connected. But unfortunately, if we do that, the rotational direction of the output shaft is going to be the same as the input shaft, because now if the input shaft rotates clockwise and the idler rotates counterclockwise, the output shaft will also rotate clockwise, so that won't work. It appears that we're going to have another idler to reverse the reversing action of the first idler and use it to drive the output shaft. Here I've added the second idler, meshing with the output gear. Now all we have to do is use the first idler to drive the second idler without conflicting with the other two gears. We can do that with a second gear on the shaft of the first idler. But since it's the same size as the output gear, it has to be on yet another plane of rotation to ensure that the gears don't conflict. In this animation, you can see the movement of the gears, and you can see that we are getting the kind of contra-rotating motion that we intended with this gear arrangement.